Out on a desert plain under the blazing sun, the air trembles like a ghost of heat. A traveler sees water shimmering ahead, a pool that seems to promise relief. Yet the closer they walk, the further it recedes, until at last it vanishes into nothingness. What they have seen is a mirage, an illusion born not of imagination, but of physics. Light, which we imagine as straight and unwavering, has bent. It has curved through layers of air at different temperatures, each with a slightly different density. The traveler's eyes and brain, built to trust straight lines of sight, are fooled by this bending, turning a trick of light into the vision of a distant lake. Such illusions are not rare. They remind us that light, though the fastest thing in the universe, is not immune to the environment through which it travels. When a straw sits in a glass of water, it appears broken, shifted at an angle where the liquid meets the air. When a rainbow arcs across the sky after rainfall, the colors fan out as sunlight bends differently for each wavelength, splitting white light into a spectrum. These familiar images, part of our daily lives, carry within them a profound truth. Light is not an untouchable straight traveler. It is obedient. It is responsive. It bends when it must. For centuries, people tried to grasp what this bending meant. Ancient philosophers argued whether light was a stream of particles or a disturbance of some medium. By the age of Newton, experiments had shown that light could reflect and refract, yet the deep reason for this behavior remained unclear. Was light bending because it was being tugged like a rope, or did it simply follow paths dictated by the properties of matter? The questions deepened as telescopes expanded human vision outward to the stars. Astronomers noticed the twinkling of stars in the night sky, a dancing effect caused by light curving through Earth's turbulent atmosphere. Again, the image we see is not the pure, straight journey of starlight, but its distortion through layers of shifting air. What these illusions reveal is simple, yet astonishing. The path of light is not fixed. It responds to the shape of space it passes through. In the air above the desert, in the glass of water, in the droplets that scatter the rainbow, space is not empty, but filled with material that guides light along new routes. If the space itself could bend, one might wonder, what then would light do? The answer came not from mirages or rainbows, but from the sky itself. In the early 20th century, Albert Einstein showed that light does not bend because of a mysterious force pulling it. Instead, light bends because it travels along the straightest possible paths in a curved geometry of space and time. This was a revolution. Instead of space being a static stage on which events unfold, Einstein revealed it as a dynamic fabric, one that mass and energy themselves can bend and shape. Light, ever loyal to geometry, follows the curvature. It does not resist. It cannot resist. The proof was not long in coming. In 1919, during a solar eclipse, astronomers observed stars near the sun appearing shifted from their normal positions. The sun's mass had curved the fabric of space-time around it, bending starlight so that it reached Earth from slightly altered directions. This was no mirage. This was gravitational lensing, the cosmos itself bending light across the vault of the sky. The universe had offered a grand experiment, and the result was clear. Light obeys space-time. Gravitational lensing has since become one of the most powerful tools in astronomy. Massive clusters of galaxies act like lenses, curving light from galaxies behind them into arcs and rings. Astronomers use these cosmic illusions to map invisible matter, revealing the presence of vast halos of dark matter that outweigh visible stars. In such moments, the bending of light is not an error of vision, but a window into the unseen. What unites a desert mirage, a straw in water, a rainbow, and the arcs of galaxies stretched across the heavens is a simple truth. Light bends because it must follow the paths allowed by its environment. On Earth, that environment is air, glass, or water. In the cosmos, it is space-time itself. Yet this realization leads to a haunting question. If light bends when space-time is curved, what of gravity itself? If gravity is not a force, but the curve of space-time, can it too bend in ways we can observe? Can gravity ripple, twist, or even fold in upon itself the way light does in a mirage or lens? That question carries us deeper, beyond the illusion of emptiness, into the true nature of gravity itself. The mirage fades, but the question it left behind grows heavier. If light bends through the play of air and water, and bends more profoundly when space-time itself is curved, then what does that mean for our understanding of reality? Our instincts tell us that straight lines should be eternal, yet light reveals again and again that straightness is only an appearance, a convenience of perception. Consider the glass of water on a table. You lower a pencil into it, and instantly the pencil appears broken, bent at the surface. You know it is not broken, and yet your eyes insist on the illusion. This is refraction, the bending of light when it passes between materials of different densities. Light slows slightly in water compared to air, and that change of speed alters its direction. The pencil has not changed, but the geometry of light's journey has. Our brains are wired to interpret light as moving in straight lines, and so we misinterpret the pencil as bent. This everyday trick echoes the much larger tricks that the cosmos plays with our perception. Sailors once feared mirages as signs of phantom lands. Travelers on desert trails believed they saw shining oases that evaporated as they approached. All of these illusions were born from light curving invisibly, its pathway shifted by temperature gradients or atmospheric layers. When air near the ground is hotter and less dense than the air above, light rays bend upward before reaching our eyes. We interpret the bent rays as coming from the ground itself, and so we imagine a pool of water. The bending is real, even if the pool is not. Now imagine the vastness of space where stars shine across unimaginable distances. In that emptiness, there is no air, no glass, no water to interfere. One might expect light to travel perfectly straight. Yet when it nears a massive object like the sun or a galaxy cluster, light again curves. This time, it is not because of density or temperature, but because mass itself bends space-time. To a photon, the tiny particle of light, the path is still the straightest possible route, but straightness itself has been redefined. The eclipse expedition of 1919 changed the course of physics forever. Astronomers journeyed to measure starlight grazing past the sun during total eclipse. If Newton was right, the sun's gravity would tug on photons like cannonballs, though only slightly. If Einstein was right, the bending would be twice as large, because it was not a tug, but a reshaping of the entire stage on which light moved. The photographs confirmed Einstein. Starlight bent exactly as predicted by general relativity. Space was not a backdrop. It was alive, curved by mass, and light was its obedient traveler. From that moment onward, astronomers could never look at the heavens the same way. Telescopes revealed arcs of light stretched into glowing halos. Galaxies multiplied into mirages across the sky. Entire maps of dark matter were sketched by tracing how invisible mass bent light from galaxies behind it. The lensing was no illusion. It was a message written by the universe, showing us where matter hides, even when it cannot be seen. The human eye evolved to trust simple paths, often struggles with such revelations. We see an arc of a galaxy and think of distortion, but in truth, the galaxy's light has taken the only possible path through a warped geometry. The bending is not an error, it is a consequence of the rules of space-time. Our perception must adapt, for the universe does not bend to our expectations. And so a new idea emerges, quiet but profound. If light bends whenever the geometry of space-time is altered, then the bending is not about light itself at all. It is about the stage on which all events unfold. Light simply reveals the structure of that stage, tracing the curves hidden from our senses. It is as if the universe were a vast invisible sculpture, and photons, moving faithfully along its lines, sketch its shape for us in strokes of brightness. This recognition changes the question. We no longer ask only why light bends. We begin to wonder, what else must bend? If gravity is the geometry itself, if mass and energy shape the very fabric of reality, then can gravity bend in its own right? Does it twist and ripple? Or is it the very definition of bending itself? From illusions on the desert floor to arcs of galaxies billions of light years away, light has shown us that straight lines are an illusion. The deeper truth lies in the curves of space-time. And at the heart of this revelation waits gravity, not as a force pulling invisibly, but as the silent architect of those curves. The bending of light is only the beginning, for it opens a doorway into a stranger world than our senses can easily accept. When you look at a star, you believe you are seeing it in its true place, but in reality, you are seeing where its light has been guided. The star's true position may be shifted ever so slightly by the gravity of bodies along the way. Every beam of starlight carries a history of bends, of curvatures encountered on its path. To us, the sky is a map. To light, it is a pilgrimage across warped terrain. Think again of the eclipse experiment of 1919. The astronomers placed their trust in fragile instruments, photographing stars, whose positions they had measured months earlier. The difference between Newton's prediction and Einstein's was tiny, measured in seconds of arc, an angle smaller than the width of a coin, held many meters away. Yet the precision of their observations revealed that space itself was curved. The triumph was not just for Einstein, but for a new way of seeing the cosmos. The universe was not built upon flat foundations. It was elastic, dynamic, capable of bending. This recognition shook more than astronomy. It challenged philosophy itself. If space could bend, if time could stretch, then the absolutes of centuries were illusions. The firm straight lines of Euclid gave way to a malleable geometry, one that responded to the weight of suns and planets. And through this geometry light traced its lines, uncomplaining, faithful to the curvature beneath it. What, then, is gravity? Newton had told us it was a force that reached invisibly across space, pulling apple to ground and planet to Sunday. His laws worked beautifully, predicting the motions of worlds with unmatched precision. But in Einstein's vision, gravity was no force at all. It was the bending of space-time itself. A planet moves around a star not because it is pulled by some invisible hand, but because it follows the natural path carved into the fabric of reality. The bending of space-time is the motion we call gravity. When light bends near a star, it is not being tugged like a stone thrown past a mountain. Instead, the space it moves through is itself curved by the star's mass, and light, loyal to straightness, follows that curve. The illusion is that light is being deflected. The reality is that light never strays from its straight path. The straightness itself is curved. This idea can feel slippery, even contradictory. We imagine straightness as absolute, yet Einstein insisted that straightness is always local. Imagine an ant crawling across a globe. To the ant, its path feels straight, yet to someone watching from above, the ant's path is curved across the sphere. In the same way, photons glide straight through their local space-time, while from our larger perspective, their paths arc around stars and galaxies. The difference is that in Einstein's cosmos, the globe is not a fixed sphere, but a living fabric, sculpted by the very mass and energy within it. From mirages in deserts to the bending of distant galaxies, light shows us again and again that our intuition of straightness is a limited tool. The truth is deeper, woven into the geometry of the universe itself. And once we accept this, the haunting question returns with greater force. If light bends along space-time, and gravity is the bending of space-time, what does it mean to say that gravity bends? Can the bending itself bend further? Can space-time ripple and twist beyond the presence of matter, carrying waves of gravity across the cosmos, the way waves of light carry illumination? The stage is set for a new leap. To ask whether gravity bends is to confront the nature of reality itself. And that is where our journey must go next, into the heart of what gravity truly island. Gravity begins as the most familiar of companions. It is there when a child lets go of a stone and watches it fall, when water pours down a stream, when the earth holds its oceans and air close so that life can flourish. It is so constant and quiet that for most of human history, it was never questioned. People spoke of objects falling because that was their nature, as if stones longed for the ground. Only with Newton did gravity emerge as something far more precise and universal, a single principle tying together the falling apple and the motion of the moon. Newton imagined gravity as a force, an invisible tether stretching across emptiness. In his mathematics, the earth pulls the apple, and the apple pulls the earth, each with equal strength. The same pull that brings the apple down also bends the path of the moon, curving its endless fall around the planet into orbit. It was a breathtaking vision, for with it, the heavens and the earth were unified. The motions of the planets were no longer divine mysteries, but consequences of the same law that ruled the simplest fall. This view of gravity as a force endured for centuries. Engineers built bridges, astronomers charted planets, navigators crossed oceans, all with confidence in Newton's equations. Yet in the corners of precision, small puzzles appeared. Mercury, the innermost planet, wandered in its orbit in ways Newton's law could not fully explain. The speed of light seemed strangely absolute, refusing to yield to the tug of Newtonian mechanics. The stage was set for a deeper truth, one that would transform gravity from a force into something even more fundamental. Einstein's revolution began not with gravity but with light. He discovered that no matter how you moved, no matter how fast, the speed of light remained constant. To preserve this constancy, time itself must stretch and space must contract. Out of this realization came special relativity, and from it grew the seeds of a new vision of gravity. If space and time could bend for the sake of light, perhaps they could bend under the weight of matter as well. In 1915, Einstein presented general relativity, a theory that swept aside the old picture of force. In this vision, mass tells space-time how to curve, and space-time tells matter how to move. A planet does not orbit because it is pulled, but because the straightest path available to it is a curve in space-time. A star does not bind its planets with invisible strings, but with the geometry of reality itself. This was not metaphor. It was mathematics written in equations as elegant as they were difficult, describing a universe where gravity is geometry. Imagine space-time as a fabric stretched taut. Place a heavy sphere upon it and the fabric dips, curving all paths nearby. Roll a smaller sphere across the surface, and it will spiral around the depression, not because it is pulled, but because that is the natural path laid out before it. Replace the fabric with four-dimensional space-time, replace the spheres with stars and planets, and you have Einstein's universe. The consequences are profound. Gravity is no longer an external agent acting upon matter. It is the very structure of space and time, responding to mass and energy. Black holes emerge naturally from the mathematics, regions where the curvature becomes so extreme that not even light can escape. The expansion of the universe itself can be seen as the stretching of space-time, driven not by forces in the old sense, but by the dynamics of the fabric itself. And yet, in embracing this new vision, a strange question arises. If gravity is the curvature of space-time, can gravity itself bend? Can the fabric that shapes all motion also be shaped in return, not only by mass, but by its own presence? The idea seems almost recursive, as if reality itself might ripple upon its own surface. Newton's picture gave us a universe of invisible tethers, each force acting independently, clear and simple. Einstein's picture gave us a universe of geometry, subtle and elegant, where matter and space are inseparable. But within that elegance hides a deeper complexity, for Einstein's equations are non-linear, meaning gravity can act upon itself. This opens the door to phenomena Newton never dreamed of, to waves of pure space-time, traveling across the cosmos. The journey ahead will take us to that threshold, to the realization that gravity is not only curvature, but also a participant in its own drama. To ask if gravity bends is to prepare to witness gravity shaping itself, folding and rippling in ways that blur the line between the stage and the play. Gravity, in Einstein's vision, is not an outside force acting across a void, but the very architecture of space and time. Yet once we accept this, a subtle realization begins to dawn. If geometry itself is the law, then gravity cannot remain passive. Geometry is not rigid, and so the shapes carved by stars and planets do not simply remain. They interact, they change, and they can even influence one another. Einstein's equations reveal this truth with startling clarity. They are nonlinear, meaning that the solutions do not merely add together like simple arithmetic. Instead, the presence of one gravitational field can alter another. This is unlike light, which travels through space without changing the medium in which it moves. Gravity, being the shape of space-time itself, has the power to act back upon its own form. It is as though a canvas could paint upon itself, creating patterns that reshape the very surface on which they are drawn. Think of two black holes locked in orbit around one another. Each curves space-time into a deep well, yet together their dance sculpts a dynamic whirlpool of geometry. They do not simply coexist. They create waves that spread outward, waves not of matter, not of energy in the conventional sense, but of space-time itself in motion. These are gravitational waves, the ripples of reality that arise when gravity bends upon gravity. For centuries, no one imagined such a thing. Newton's universe was clockwork, each force adding neatly to the next, each orbit a balance of predictable pulls. But Einstein's universe is alive with feedback. Mass shapes space-time shapes mass, and even space-time alone can carry waves of curvature far from their source. The possibility was so radical that even Einstein himself doubted whether these waves could ever be detected. They seemed destined to remain theoretical, whispers, too faint to ever be heard. And yet they were real, and in time humanity would learn to listen. The bending of light had shown us the shape of space-time around stars and galaxies. The bending of gravity itself promised to show us something deeper, the very music of space-time, a chorus played when massive objects collide. The thought is almost overwhelming. If gravity is geometry, and geometry itself can ripple, then the universe is not merely a stage, but also a symphony, one that resonates through the curvature of reality. From black holes spiraling into one another to the violent births of neutron stars, these ripples race across the cosmos at the speed of light, unattenuated, unbroken. They carry with them the direct signature of the events that created them, not distorted by dust or gas, not bent like light, but pure imprints of the most extreme dances of gravity. They are proof that gravity does not merely bend other things, it bends itself. And so we arrive at a threshold. If gravity can ripple, if it can carry waves of its own curvature across billions of light years, then the universe offers us more than vision. It offers us hearing, the chance to listen to space-time itself. This will lead us to the most remarkable confirmation of Einstein's vision, the moment when instruments on Earth caught the faint tremor of two black holes merging, and humanity heard the sound of gravity bending itself across the cosmos. Gravity acting on itself is one of the most difficult ideas to hold in the mind, because it demands that we abandon the image of a simple stage where forces play their roles. Instead, the stage itself is alive. Imagine a pair of black holes, each one a chasm of space-time where geometry has folded inward. Alone, each is silent, holding its secrets behind an event horizon. But together, orbiting closer and closer, they stir space-time into motion. Their mutual embrace does not just shape their own immediate surroundings, it radiates waves outward, waves of pure geometry spreading through the universe. To picture this, think of ripples upon a pond when stones are thrown in. The water is not carrying objects away, but the surface itself rises and falls, transmitting energy outward. Gravitational waves are like this, though immeasurably more subtle. They are not disturbances upon a medium. They are disturbances of the medium. They are space-time itself stretching and compressing as the waves pass. No matter is required, no air, no water. The fabric of reality is sufficient, and it is flexible. This is the ultimate expression of gravity bending. It is not bending light, nor bending the path of planets. It is bending itself, folding its geometry into waves that speed across the cosmos. These waves are not mere curiosities. They carry with them the fingerprints of the events that created them, the masses and motions of black holes or neutron stars that spiraled together. Where light can be absorbed or scattered, gravitational waves pass unimpeded, carrying pristine information from places no light can ever emerge. The mathematics of this process is daunting, but the principle is simple. When masses accelerate in certain ways, particularly in asymmetric spirals or collisions, they shake space-time itself. That shaking radiates outward at the speed of light. For decades, these waves remained hidden, too faint to be sensed. Even Einstein wondered if they would ever be observed. Yet, the equations left no doubt. If general relativity was true, the waves must exist. Astronomers began to look for indirect signs. In the 1970s, a binary pulsar was discovered, two neutron stars orbiting each other with extraordinary precision. Over time, their orbit was seen to decay, the two stars spiraling closer at exactly the rate predicted if they were losing energy through gravitational waves. It was a silent confirmation, a whisper of waves too faint to touch us but powerful enough to alter the lives of stars. The stage was set for something greater. If instruments could be built sensitive enough, they could capture the passing tremors of space-time itself. Humanity could, at last, listen to gravity. The task seemed impossible. The ripples expected from distant black holes would stretch and compress space on Earth by less than the width of a proton. Yet engineers and physicists dared to attempt it, constructing lasers and mirrors in tunnels kilometers long, designed to measure impossibly small shifts in distance. This was not merely a test of technology, it was a test of the nature of gravity itself. For if the instruments heard nothing, then Einstein's equations might be incomplete. But if they heard the faint chirp of colliding black holes, it would prove that gravity bends in the deepest possible sense. It would prove that space-time itself can ripple. Thus, by the end of the 20th century, the question was no longer whether gravity bends, but whether we would ever be able to hear its bending. The answer would come, and it would change how humanity understood the universe forever. Gravity does not only shape the paths of planets or the bending of light. In Einstein's vision, it can also shape itself. This is perhaps the strangest leap of all, because it asks us to imagine not a force acting on matter, but a fabric so alive that it can ripple and stir even in the absence of anything else. If space-time can bend, then surely those bends can shift and spread, carried outward, like echoes through a cathedral. This is the world of self-interaction, where gravity becomes both actor and stage, sculptor and sculpture. The key lies in the equations Einstein wrote down in 1915. These were not simple, linear rules, where one influence can be neatly added to another. Instead, they were non-linear, which means that the presence of one curvature of space-time can influence another curvature nearby. In other words, gravity can act on gravity. This is not obvious at first. When you think of light, you imagine beams passing through one another without interference. But gravitational fields are different. They are not passengers in space. They are space. And so when two great curvatures overlap, they do not pass cleanly by. They combine, they interact, they change the fabric around them. To see this in action, imagine two black holes locked in an embrace. Each one is a distortion of space-time so extreme that not even light can escape. When they orbit one another, their combined gravity does more than simply hold them together. Their motion stirs the fabric of space-time, setting off ripples that race outward across the cosmos. These ripples are not sound, not light, not matter. They are gravity itself in motion, space-time bending and unbending as the waves pass. This is gravity acting on itself. The black holes are the source, but the waves they create are pure gravity, carrying energy away from the system. The holes spiral closer as they lose this energy, their orbit tightening until they finally merge into one. The finale of their dance is a burst of gravitational radiation so intense that for a brief instant it carries more power than all the stars in the observable universe combined. Yet those waves are invisible, silent, passing through galaxies, through stars, through you and me, leaving only the tiniest tremor behind. For centuries, nothing like this could even be imagined. Newton's laws saw gravity as a static tether, pulling but never changing itself. Einstein's equations opened a door to a dynamic cosmos, where gravity was geometry and geometry could ripple. But even Einstein wondered whether such ripples would ever be more than mathematical curiosities. Could they really exist as physical waves, or were they only abstractions, artifacts of the equations? The universe itself provides the answer. Whenever two massive objects orbit one another, two black holes, two neutron stars, even two white dwarfs, they radiate gravitational energy. It is not a choice. It is inevitable, the natural consequence of motion in curved space-time. Just as accelerating charges radiate electromagnetic waves, accelerating masses radiate gravitational waves. The difference is scale. To produce a wave strong enough to reach us, the masses must be immense, and the motion violent. Black holes and neutron stars are the perfect engines for this cosmic music. The most stunning part of this realization is that gravity, the architect of space-time, is also one of the few things that can escape the grip of a black hole. Light cannot, matter cannot, but gravitational waves, being distortions of space-time itself, are not trapped in the same way. They emerge from the maelstrom, racing outward at the speed of light, carrying with them the story of what happened at the very edge of the unknowable. When we ask if gravity bends, the truth is that it does not merely bend others, it bends itself. It produces waves that stretch and compress the universe in rhythmic pulses. These waves are unimaginably faint by the time they reach Earth, stretching distances by less than the width of a proton. Yet they carry with them the tale of some of the most powerful events in the universe, events that would otherwise remain hidden forever. This leads us to the threshold of discovery. For decades, the existence of gravitational waves was accepted in theory, confirmed indirectly by the slow dance of neutron stars, whose orbits shrank exactly as predicted. But no one had yet touched them directly. No one had yet felt the tremor of spacetime itself. To achieve that would require an instrument unlike any built before, one capable of measuring changes in length so small they defy imagination. Humanity would try, and against the odds, succeed. The story of gravity bending itself is therefore not just theoretical. It is real, and it is something we have now heard with our own instruments. The universe spoke through the ripples of space-time, and for the first time in history, we listened. The idea of gravity acting upon itself long seemed too exotic to believe, and yet the cosmos provided hints, faint at first, but undeniable. In the 1970s, two astronomers, Russell Hulse and Joseph Taylor, discovered a system unlike any known before. It was a binary pulsar, two neutron stars locked in a dizzying orbit around one another. Neutron stars are the remnants of massive suns, collapsed to spheres only a dozen kilometers across, yet so dense that a single teaspoon of their matter would outweigh a mountain. Their orbits around one another were measured with exquisite precision by tracking the radio pulses emitted from one of the stars. Over years of observation, Hulse and Taylor found that the orbit was shrinking. The stars were drawing ever closer, in a slow spiral. No force in Newton's universe could explain this, but in Einstein's it was expected. The system was radiating energy away as gravitational waves, ripples of space-time itself, carrying energy into the cosmos. The rate of orbital decay matched Einstein's equations perfectly. It was as though the binary was whispering to us across the light years, confirming that gravity can ripple, that it can bend itself into waves. This discovery earned the Nobel Prize, for it was the first firm evidence that gravitational waves were more than abstractions. Still, whispers are not the same as a song. Indirect evidence was powerful, but incomplete. Physicists yearned for direct detection, for the actual tremor of space-time to be measured on Earth. The challenge seemed impossible. The ripples that reach our planet from distant collisions stretch and compress distances by less than 1,000th of the diameter of a proton. No ruler, no telescope, no ordinary device could detect such changes. Yet the ambition grew. The idea was deceptively simple. If a gravitational wave passes through Earth, it will stretch space in one direction while compressing it in another. If two long tunnels are placed at right angles to each other, with laser beams bouncing back and forth inside them, the passing wave would change the distances in those tunnels ever so slightly, altering the interference of the light. The pattern would shift, revealing the passage of the wave. This idea became reality in the form of the Laser Interferometer Gravitational Wave Observatory, or LIGO. Constructed with arms 4 kilometers long, its mirrors polished to impossible precision, its lasers stabilized against the faintest vibrations. LIGO was designed to listen to the universe in a way no instrument ever had. The noise of trucks, the tremor of earthquakes, even the footsteps of workers could overwhelm the signal, and so every detail was refined to isolate the faintest possible whisper of space-time. For years, the detectors listened and heard nothing but silence, and many wondered if the dream was futile. Yet persistence drove the project forward. Upgrades refined the sensitivity, and hope remained that somewhere in the depths of space, two massive objects were spiraling together and would send their waves our way. Then, in September of 2015, the silence broke. The signal was brief, less than a second long. It was the final dance of two black holes, each about 30 times the mass of our Sun, merging more than 1 billion light-years away. The waves reached Earth after traveling across cosmic time, stretching and compressing space-time itself as they passed through the detectors. For the first time, humanity had heard the bending of gravity. The signal matched Einstein's predictions exactly. The chirp of the black hole's merger confirmed that gravity is not just the curvature of space-time, but a living fabric capable of rippling across the universe. In that moment, general relativity was affirmed in its most daring prediction, and a new era of astronomy began. This was gravity not only bending light, not only guiding planets, but bending itself, sending out ripples that spoke of catastrophic collisions in places no light could ever reach. Black holes merging in darkness had become visible not with eyes, but with ears attuned to space-time. The discovery was a triumph not only of theory but of perseverance, of decades of work by thousands of scientists and engineers who trusted Einstein's equations enough to build an instrument sensitive to tremors in the fabric of reality. It proved beyond doubt that gravity acts on itself, bending and rippling, carrying information across the cosmos at the speed of light. But this discovery also raised new questions. If gravity can ripple, how else can it behave? Can it twist and fold in ways we have not yet imagined? And if light and gravity both bend, do they bend in the same way? Or does gravity conceal deeper layers of reality yet to be uncovered? The faint chirp that reached Earth in 2015 was more than a scientific milestone. It was the first voice of the universe in a language older than light. For billions of years, those waves had traveled silently, unaffected by dust or gas, untouched by the obstacles that blur or block starlight. When they finally brushed against our planet, they left a trace so slight it could be measured only by an instrument built with almost impossible precision. Yet within that trace lay the memory of two black holes colliding in darkness. Humanity had heard space-time itself ring like a bell. This was not a single triumph, but the opening of a new sense. Until then, astronomy had been almost entirely visual. We studied stars by their light, galaxies by their glow, nebulae by their colors. Even when we extended our view to radio waves or X-rays, we were still working with photons, with the messengers of electromagnetism. Now we had a new messenger, one that did not come from outside space-time, but from space-time itself. Gravitational waves opened a window that no photon could provide. The discoveries multiplied. More black hole mergers were heard, each signal unique, each telling a story of masses and spins and distances. Then came the detection of two neutron stars colliding. This event was accompanied not only by gravitational waves but by light across the spectrum, from gamma rays to radio waves. For the first time, the cosmos gave us both sight and sound of the same event. The waves carried the imprint of the star's spiral, while the light revealed the fireball of elements flung outward. Heavy atoms like gold and platinum were forged in that collision, seeding the universe with the materials that would one day form planets and people. Through these detections, the nonlinear nature of Einstein's equations became undeniable. Gravity does not simply curve around matter. It can carry away energy. It can transmit information. It can act back upon itself in ways Newton could never have imagined. The waves we now observe are the proof that gravity bends, not in the way light bends through glass or around stars, but in a deeper sense, It is the bending of the fabric of reality, shaking itself loose and sending ripples into the void. Each signal detected by LIGO and later by other observatories like Virgo is a reminder that the universe is restless. Black holes collide, neutron stars spiral inward, entire galaxies merge, and through all of it, space-time ripples. These waves are faint by the time they reach us, yet they are everywhere. The Earth is awash in them, passing unnoticed through our bodies, through the planet, through the atmosphere. Only our instruments, finely tuned and patient, reveal their presence. And so we come to a new understanding. Gravity is not just the geometry of space-time shaped by mass. It is dynamic, alive, capable of bending and bending again, producing waves that travel freely through the cosmos. To ask whether gravity bends is no longer a question of speculation. The answer is written in the data, recorded in the trembling of mirrors, confirmed in the mathematics that has never yet failed. But this answer leads to another. If gravity can ripple outward, what happens in the most extreme environments, where space-time is bent to its breaking point? Black holes have given us waves and whispers, but at their centers lie singularities, places where our understanding falters. To explore whether gravity can fold entirely in upon itself, to see whether the bending has a limit, we must venture into the realm of black holes. On a quiet morning in September of 2015, a faint vibration passed through Earth. It was not felt by people, nor by animals, nor even by the most sensitive seismographs. It was far too subtle for ordinary instruments, stretching and squeezing space itself by less than the width of a proton. Yet in two long tunnels in Louisiana and Washington, beams of laser light noticed. They flickered, shifted, and sang the first note of a cosmic chorus. Humanity had, for the first time, heard the ripples of space-time itself. The story of this moment is as much about patience as it is about discovery. For a century after Einstein's prediction of gravitational waves, no one could be sure they would ever be measured. The waves were real in the mathematics, confirmed indirectly by the slow spiraling of neutron stars, but to catch them directly seemed impossible. They passed through planets and stars as though through air, leaving only the tiniest mark. To hear them, scientists had to build machines capable of detecting distortions smaller than anything ever attempted, changes in distance thousands of times smaller than the nucleus of an atom. This machine was LIGO, the Laser Interferometer Gravitational Wave Observatory. It was not one but two instruments, separated by thousands of kilometers, each with arms 4 kilometers long. Lasers bounced between mirrors in vacuum tubes, comparing distances with impossible accuracy. When a gravitational wave passed, it would stretch one arm and compress the other, shifting the interference pattern of the light. By comparing the signals from both detectors, scientists could confirm that what they heard was not local noise, but a true tremor of space-time sweeping across Earth. The signal they caught came from the death spiral of two black holes. Each one was about 30 times the mass of our Sun, locked in orbit around one another more than 1 billion light-years away. For millions of years they had circled, but as they lost energy through gravitational waves, they drew closer and closer, until, in their final seconds, they whirled at nearly the speed of light before colliding and merging into one. The collision released an energy equivalent to several suns converted entirely into gravitational waves in a fraction of a second. It was this storm of curvature that traveled across the universe and reached Earth on that September morning. The waveform recorded by LIGO was distinctive. It began as a low thrum, rising in pitch and amplitude as the black holes spiraled faster, ending in a sharp chirp as they merged. In less than a second, the detectors had captured a story written over billions of years and billions of light years, carried faithfully across the void by space-time itself. When the announcement came in February of 2016, the scientific world and the public alike were electrified. The discovery was hailed as one of the greatest of our age, confirming Einstein's prediction from 1916 and opening a new era of astronomy. For the first time, we had more than sight. We had hearing. The universe had been silent to us, but now we could listen to its deepest cataclysms. The confirmation was not just about proving a theory. It was about expanding the very toolkit of humanity. Telescopes show us photons. The mess out on a desert plain under the blazing sun. The air trembles like a ghost of heat. A traveler sees water shimmer red, a pool that seems to promise relief. Yet the closer they walk, the further it recedes, until at last it vanishes into nothingness. What they have seen is a mirage, an illusion born not of imagination, but of physics. Light, which we imagine as straight and unwavering, has bent. It has curved through layers of air at different temperatures, each with a slightly different density. The traveler's eyes and brain, built to trust straight lines of sight, are fooled by this bending, turning a trick of light into the vision of a distant lake. Such illusions are not rare. They remind us that light, though the fastest thing in the universe, is not immune to the environment through which it travels. When a straw sits in a glass of water, it appears broken, shifted at an angle where the liquid meets the air. When a rainbow arcs across the sky after rainfall, the colors fan out as sunlight bends differently each wavelength, splitting white light into a spectrum. These familiar images, part of our daily lives, carry within them a profound truth. Light is not an untouchable straight traveler. It is obedient. It is responsive. It bends when it must. For centuries, people tried to grasp what this bending meant. Ancient philosophers argued the light was a stream of particles or a disturbance of some medium. By the age of Newton, experiments had shown light could reflect and refract, yet the deep reason for this behavior remained unclear. Was light bending because it was being tugged rope, or did it simply follow paths dictated properties of matter? The questions deepened as telescopes expanded human vision outward to the stars. Astronomers noticed the twinkling of stars in the night sky, a dancing effect caused by light curving through Earth's turbulent atmosphere. The image we see is not a pure straight journey of starlight, but its distortion through layers of shifting air. What these illusions reveal is simple, yet astonishing. The path of light is not fixed. It responds to the shape of space it passes through. In the air above the desert, in the glass of water, droplets that scatter the rainbow, space is not empty, but filled with material that guides light along new routes. If the space itself could bend, one might wonder, what then would light do? The answer came not from mirages or rainbows, but from the sky itself. In the early 20th century, Albert Einstein showed that light does not bend because of a mysterious force pulling it. Instead, light bends because it travels along the straightest possible paths in a curved geometry of space and time. This was a revolution. Instead of space being a static stage events unfold, Einstein revealed it as a dynamic fabric, one that mass and energy themselves can bend and shape. Light, ever loyal to geometry, follows the curvature. It does not resist. It cannot resist. The proof was not long in coming. In 1919, during a solar eclipse, astronomers observed stars near the sun appearing shifted from their normal positions. The sun's mass had curved the fabric of space-time around it, bending starlight so that it reached Earth from slightly altered directions. This was no mirage. This was gravitational lensing, the cosmos itself bending light across the vault of the sky. The universe had offered a grand experiment, and the result was clear. Light obeys space-time. Gravitational lensing has since become one of the most powerful tools in astronomy. Massive clusters of galaxies act like lenses, curving light from galaxies behind them in arcs and rings. Astronomers use these cosmic illusions to map invisible matter, revealing the presence of vast halos of dark matter that outweigh visible stars. In such moments, the bending of light is not an error of vision, but a window into the unseen. What unites a mirage, a straw in water, a rainbow, and the arcs of galaxies stretched across the heavens is a simple truth. Light bends because it must follow the paths allowed by its environment. On Earth, that environment is air, glass, or water. In the cosmos, it is space-time itself. Yet this realization leads to a haunting question. If light bends when space-time is curved, what of gravity itself? If gravity is not a force, but the curve of space-time. Can it too bend in ways we can observe? Can gravity ripple, twist, or even fold in upon itself the way light does in a mirage or lens? That question carries us deeper, beyond the illusion of emptiness, into the true nature of gravity itself. The mirage fades, but the question left behind grows heavier. If light bends through the play of air and water, and bends more profoundly when space-time itself is curved, then what does that mean for our understanding of reality? Our instincts that straight lines should be eternal, yet light reveals again and again that straightness is only an appearance, a convenience of perception. Consider the glass of water on a table. You lower a pencil into it, and instantly the pencil appears broken, bent at the surface. You know not broken, and yet your eyes insist on the illusion. This is refraction, the bending of light when it passes between materials of different densities. Light slows slightly in water compared to air, and that change of speed alters its direction. The pencil has not changed, but the geometry of light's journey has. Our brains are wired to interpret light as moving in straight lines, and so we misinterpret the pencil as bent. This everyday trick echoes the much larger tricks that the cosmos plays with our perception. Sailors once feared mirages as phantom lands. Travelers on desert trails believed they saw shining oases that evaporated as they approached. All of these illusions were born from light curving invisibly, its pathway shifted by temperature gradients or atmospheric layers. When air near the ground is hotter and less dense than the air above, light rays bend upward before reaching our eyes. We interpret the bent rays as coming from the ground itself, and so we imagine a pool of water. The bending is real, even if the pool is not. Now imagine the vastness of space where stars shine across unimaginable distances. In that emptiness, there is no air, no glass, no water to fear. One might expect light to travel perfectly straight. Yet when it nears a massive object like the sun or a galaxy cluster, light again curves. This time, it is not because of density or temperature, but because mass itself bends space-time. To a photon, the tiny part of light, the path is still the straightest route, but straightness itself has been redefined. The Eclipse expedition of 1919 changed the course of physics forever. Astronomers journeyed to measure starlight grazing past the sun during total eclipse. If Newton was right, the sun's gravity would tug on photons like cannonballs, though only slightly. If Einstein was right, the bending would be twice as large, because it was not a tug, but a reshaping of the entire stage on which light moved. The photographs confirmed Einstein. Starlight bent exactly as predicted by general relativity. This was not a backdrop. It was alive, curved by mass, and light was its obedient traveler. From that moment onward, astronomers could never look at the heavens the same way. Telescopes revealed arcs of light, stretched into glowing halos. Galaxies multiplied into mirages across the sky. Entire maps of dark matter were sketched by tracing how invisible mass bent light from galaxies behind it. The lensing was no illusion. It was a message written by the universe, showing us where matter hides, even when it cannot be seen. Human eye evolved to trust simple paths, often struggles with such revelations. We see an arc of a galaxy and think of distortion. But in truth, the galaxy's light has taken the only possible path through a warped geometry. The bending is not an error, it is a consequence of the rules of space-time. Our perception must adapt. The universe does not bend to our expectations, and so a new idea emerges, quiet but profound. If light bends whenever the geometry of space-time is altered, then the bending is not about light itself at all. It is about the stage all events unfold. Light simply reveals the structure of that stage, tracing the curves hidden from our senses. It is as if the universe were a vast invisible sculpture, and photons, moving faithfully along its lines, sketch its shape for us in strokes of brightness. This recognition changes the question. We no longer ask only why light bends. We begin to wonder, what else must bend? If gravity is the geometry itself, If mass and energy shape the very fabric of reality, then can gravity bend in its own right? Does it twist and ripple? Or is the very definition of bending itself? From illusions on the desert floor to arcs of galaxies billions of light years away, light has shown us that straight lines are an illusion. The deeper truth lies in the curves of space-time. And at the heart of this revelation waits gravity, not as a force pulling invisibly, but as the silent architect of those curves. The bending of light is only the beginning, for it opens a doorway into a stranger world than our senses can easily accept. When you look at a star, you believe you are seeing it in its truths, but in reality, you are seeing where its light has been guided. The star's true position may be shifted ever so slightly by the gravity of bodies along the way. Every beam of starlight carries a history of bends, of curvatures encountered on its path. To us, the sky is a map. To light, it is a pilgrimage across warped terrain. Thinking of the eclipse experiment of 1919, the astronomers placed their trust in fragile instruments, graphing stars, whose positions they had measured months earlier. The difference between Newton's prediction and Einstein's was tiny, measured in seconds of arc. An angle small than the width of a coin held many meters away. Yet the precision of their observations revealed that space itself was curved. The triumph was not just for Einstein, but for a new way of seeing the cosmos. The universe was not built upon flat foundations. It was elastic, dynamic, capable of bending. This recognition shook more than enemy. It challenged philosophy itself. If space could bend, if time could stretch, then the absolutes of centuries were illusions. The firm straight lines of Euclid gave way to a malleable geometry, one that responded to the weight of suns and planets. And through this geometry light traced its lines, uncomplaining, faithful curvature. Beneath, what, then, is gravity? Newton had told us it was a force that reached invisibly across space, pulling apple to ground and planet to Sunday. His laws worked beautifully, predicting the motions of worlds with unmatched precision. But in Einstein's vision, gravity was no force at all. It was the bending of time itself. A planet moves around a star not because it is pulled by some invisible hand, but follows the natural path carved into the fabric of reality. The bending of space-time is the motion we call gravity. When light bends near a star, it is not being tugged like a stone thrown past a mountain. Instead, the space it moves through is itself curved by the star's mass, and light, law of straightness, follows that curve. The illusion is that light is being deflected. The reality is that light never strays from its straight path. The straightness itself is curved. This idea can feel slippery, even contradictory. We imagine stress as absolute, yet Einstein insisted that straightness is always local. Imagine an ant crawling across a globe. To the ant, its path feels straight, yet to someone watching from above, the ant's path is curved across the sphere. In the same way, photons glide straight through their local spacetime, while from our larger perspective, their paths arc around stars and galaxies. The difference is that in Einstein's cosmos, the globe is not a fixed sphere, but a fabric, sculpted by the very mass and energy within it. From mirages in deserts to the bending of distant galaxies, light shows us again and again that our intuition of straightness is a limited tool. The truth is deeper, woven into the geometry of the universe itself. And once we accept this, the haunting question returns with greater force. If light bends along time, and gravity is the bending of space-time, what does it mean to say that gravity bends? Can the bend itself bend further? Can space-time ripple twist beyond the presence of matter, carrying waves of gravity across the cosmos, the way waves of light carry illumination? The stage is set for a new leap. To ask whether gravity bends is to confront the nature of reality itself. And that is where our journey must go next. Into the heart of what gravity truly island. Gravity begins as the most familiar of companions. It is there when a child lets go of a stone and watches it fall, when water pours down a stream, when the earth holds its oceans and air close so that life can flourish. It is so constant and quiet that for most of human history, it was never questioned. People spoke of objects falling because that was their nature, as if stones longed for the ground. Only with Newton did gravity emerge as something far more precise and universal, a single principle tying together the falling apple and the motion of the moon. Newton imagined gravity as a force, visible tether stretching across emptiness. In his mathematics, the earth pulls the apple, and the apple pulls the earth, each with equal strength. The same pull brings the apple down also bends the path of the moon, curving its endless fall around the planet into orbit. It was a breathtaking vision, for with it, the heavens and the earth were unified. The motions of the planets were no longer divine mysteries, but consequences of the same law that ruled the simplest fall. This view of gravity as a force endured for centuries. Engineers built bridges, astronomers charted planets, navigators crossed oceans, all with confidence in Newton's equations. Yet in the corners of precision, small puzzles appeared. Mercury, the innermost planet, wandered in its orbit in ways Newton's law could not fully explain. The speed of light seemed strangely absolute, refusing to yield to the tug of Newtonian mechanics. The stage was set for a deeper truth, one that would transform gravity from a force into something even more fundamental. Einstein's revolution began not with gravity but with light. He discovered that no matter how you moved, no matter how fast, the speed of light remained constant. To preserve this constancy, time itself must stretch and space must contract. Out of realization came special relativity, and from it grew the seeds of a new vision of gravity. If space and time could bend for the sake of light, perhaps they could bend under the weight of matter as well. In 1915, Einstein presented general relativity, a theory that swept aside the old picture of force. In this vision, mass tells space-time how to curve, and space-time tells matter how to move. A planet does not orbit because it is pulled, but because the straightest path available to it is a curve in space-time. A star does not bind its planets with invisible strings, but with the geometry of reality itself. This was not metaphor. It was mathematics written in equations as elegant as they were difficult, describing a universe where gravity is geometry. Imagine space-time as a fabric stretched taut. Place a heavy sphere upon it and the fabric dips, curving all paths nearby. Pull a smaller sphere across the surface, and it will spiral around pressure, not because it is pulled, but because that natural path laid out before it. Replace the fabric with four-dimensional space-time. Replace the spheres with stars and planets, and you have Einstein's universe. The consequences are profound. Gravity is no longer an external agent acting upon matter. It is the very structure of space and time, responding to mass and energy. Black holes emerge naturally from the mathematics, regions where the curvature becomes so extreme that not even light can escape. The expansion of the universe itself can be seen as the stretching of space-time, driven not by forces in the old sense, but by the dynamics of the fabric itself. And yet, in embracing this new vision, a strange question arises. If gravity is the curvature of space-time, can gravity itself bend? Can the fabric that shapes all motion also be shaped in return, not only by mass, but by its own presence? The idea seems almost recursive, as if reality itself might ripple upon its own surface. Newton's picture gave us a universe of invisible tethers, each force acting independently, clear and simple. Einstein's picture gave us a universe of geometry, subtle and elegant, where matter and space are inseparable. But within that elegance hides a deeper complexity. For Einstein's equations are non-linear, meaning gravity can act upon itself. This opens the door to phenomena Newton never dreamed of, to waves of pure space traveling across the cosmos. The journey ahead will take that threshold to the realization that gravity is not only curvature, but also a participant in its own drama. To ask if gravity bends is to prepare to witness gravity shaping itself, folding and rippling in ways that blur the line between the stage and the play. Gravity, in Einstein's vision, is not an outside force acting across a void, but the very architecture of space and time. Yet once we accept this, a subtle realization begins to dawn. If geometry itself is the law, then gravity cannot remain passive. Geometry not rigid, and so the shapes carved by stars and planets do not simply remain. They interact, they change, and they can even influence one another. Einstein's equations reveal this truth with startling clarity. They are nonlinear, meaning that the solutions do not merely add together like simple arithmetic. Instead, the presence of one gravitational field to another. This is unlike light, which travels through space without changing the medium in which it moves. Gravity, being the shape of spacetime itself, has the power to act back upon its form. It is as though a canvas could paint upon itself, creating patterns that reshape the very surface on which they are on. Think of two black holes locked in orbit around one another. Each curves spacetime into a deep well. Together, their dance sculpts a dynamic whirlpool of geometry. They do not simply coexist. They create waves that spread outward. Waves not of matter, not of energy, in the conventional sense, of space-time itself in motion. These are gravitational waves, the ripples of reality that arise when gravity bends upon gravity. For centuries, no one imagined such a thing. Newton's universe clockwork, each force adding neatly to the next, each orbit a balance of predictable pulls. Einstein's universe is alive with feedback. Mass shapes spacetime, spacetime shapes mass, and even spacetime alone can carry waves of curvature far from their source. The possibility was so real that even Einstein himself doubted whether these waves could ever be detected. They seemed destined to remain theoretical, whispers, too faint to ever be heard. And yet they were real, and in time humanity would learn to listen. The bending of light had shown us the shape of spacetime around stars and galaxies. The bending of gravity itself promised to show us something deeper, the very music of spacetime, a chorus play when massive objects collide. The thought is almost overwhelming. If gravity is geometry, and geometry itself can ripple, the universe is not merely a stage, but also a symphony, one that resonates curvature of reality. From black holes spiraling into one another to the violent births of neutrons, these ripples race across the cosmos at the speed of light, unattenuated, unbroken. They carry with them the direct signature of the events that created them, not distorted by dust or gas, meant like light, but pure imprints of the most extreme dances of gravity. They are proof that gravity does not merely bend other things, it bends itself. And so we arrive at a threshold. If gravity can ripple, if it can carry waves of its own curvature across billions of light years, then the universe offers us more than vision. It offers us hearing, the chance to listen to spacetime itself. This will lead us to the most remarkable confirmation of Einstein's vision, the moment when instruments on Earth caught the faint tremor of two black holes merging, and humanity heard the sound of gravity bending itself across the cosmos. Gravity acting on itself is one of the most difficult ideas to hold in the mind, because it demands that we abandon the image of a simple stage where forces play their roles. Instead, the stage itself is alive. Imagine a pair of black holes, each one a chasm of space-time where geometry has folded inward. Alone, each is silent, holding its secrets behind an event horizon. But together, orbiting closer and closer, they stir space-time in motion. Their mutual embrace does not just shape their own immediate surroundings, it radiates waves outward, waves of pure geometry through the universe. To pictures, think of ripples upon a pond when stones are thrown in. Water is not carrying objects away, but the surface itself rises and falls, transmitting energy outward. Gravitational waves are like this, though immeasurably more subtle. They are not disturbance on a medium, they are disturbance of the medium. They are space-time itself stretching and compressing as the waves pass. No matter is required, no air, no water. The fabric of reality is sufficient, and it is flexible. This is the ultimate expression of gravity bending. It is not bending light, nor bending the path of planets. It is bending itself, folding its geometry into waves that speed across the cosmos. These waves are not mere curiosities. They carry with them the fingerprints of the events that created them, the masses and motions of black holes or neutron stars that spiraled together. Where light can be absorbed or scattered, gravitational waves pass unimpeded, carrying pristine information from places no light can ever emerge. The mathematics of this process is daunting, but the principle is simple. When masses accelerate in certain ways, particularly in asymmetric spirals or collisions, they shake space-time itself. That shaking radiates outward at the speed of light. For decades, these waves remained hidden, too faint to be sensed. Even Einstein wondered if it would ever be observed. Yet, the equations left no doubt. If general relativity was true, the waves must exist. Astronomers began to look for signs. In the 1970s, a binary pulsar was discovered, two neutron stars orbiting each other with extraordinary precision. Over time, their orbit was seen to decay, the two stars spiraling closer at exactly the rate predicted. If they were losing energy through gravitational waves, it was a silent confirmation, a whisper of waves too faint to touch us but powerful enough to alter the lives of stars. The stage was set for something greater. If instruments could be built sensitive enough, they could capture the past tremors of space-time itself. Humanity could, at last, listen to gravity. The task seemed impossible. The ripples expected from distant black holes would stretch and compress space on Earth by less than the width of a proton. Yet engineers and physicists dared to attempt it, constructing lasers and mirrors in tunnels kilometers long, designed to measure impossibly small shifts in distance. This was not merely a test of technology, it was a test of the nature of gravity itself. For if the instruments heard nothing, Einstein's equations might be incomplete. But if they heard the faint chirp of colliding black holes, it would prove that gravity bends in the deepest possible sense, would prove that space-time itself can ripple. Thus, by the end of the 20th century, the question was no longer whether gravity bends, but whether we would ever be able to hear bending. The answer would come, and it would change how humanity understood the universe forever. Gravity does not only shape paths of planets or the bending of light. In Einstein's vision, it can also shape itself. This is perhaps the strangest leap of all. It asks us to imagine not a force acting on matter, but a fabric so alive that it can ripple and stir even in the absence of anything else. If space-time can bend, then surely those bends can shift and spread, carried outward, like echoes through a cathedral. This is the world of self-interaction, where gravity becomes both actor and stage, sculptor and sculpture. The key lies in the equations Einstein ran in 1915. These were not simple, linear rules. One influence can be neatly added to another. Instead, they were non-linear, which means that the presence of one curvature of time can influence another curvature nearby. In other words, gravity can act on gravity. This is not obvious at first. When you think of light, you imagine beams passing through one another without interference. But gravitational fields are different. They are not passengers in space. They are space. And so when two great curvatures overlap, they do not pass cleanly by. They combine, they interact, they change the fabric around them. To see this in action, imagine two black holes locked in an embrace. Each one is a distortion of space-time so extreme that not even light can escape. When they orbit one another, their combined gravity does more than simply hold them together. Their motion stirs the fabric of space-time, setting off ripples that race outward across the cosmos. These ripples are not sound, not light, not matter. They are gravity itself in motion, space-time bending and unbending as the waves pass. This is gravity acting on itself. The black holes are the source, but the waves they create are pure gravity, carrying energy away from the system. The holes spiral closer as they lose this energy, their orbit tightening until they finally merge into one. The finale of their dance is a burst of gravitational radiation so intense that for a brief instant it carries more power than all the stars in the observable universe combined. Yet those waves are invisible, silent, passing through galaxies, through stars, through you and me, leaving only the tiniest tremor behind. For centuries, nothing like even be imagined. Newton's laws saw gravity as a static tether, pulling but never changing itself. Einstein's equations opened a door to a dynamic cosmos, where gravity was geometry and geometry could ripple. But even Einstein wondered, whether such ripples would ever be more than mathematical curiosities. Could they really exist as physical waves, or were they only abstractions, artifacts of the equations? The universe itself provides the answer. Whenever two massive objects orbit one another, two black holes, two neutron stars, even two white dwarfs, they radiate gravitational energy. It is not a choice. It is inevitable, the natural consequence of motion in curved space-time. Just as accelerating charges radiate electromagnetic waves, accelerating masses radiate gravitational waves. The difference is scale. To produce a wave strong enough to reach us, the masses must be immense, and the motion violent. Black holes and neutron stars are the perfect engines for this music. The most stunning part of this realization is that gravity, the architect of space-time, is also one of the few things that can escape the grip of a black hole. Light cannot, matter cannot, but gravitational waves, being distortions of space-time itself, are not trapped in the same way. They emerge from the maelstrom, racing outward at the speed of light, carrying with them the story of what happened at the very edge of the unknowable. When we ask if gravity bends, the truth is that it does not merely bend others, it bends itself. It produces waves that stretch and compress the universe in rhythmic pulses. These waves are unimaginably faint by the time they reach Earth, stretching distances by less than the width of a proton. Yet they carry with them the tale of some of the most powerful events in the universe, events that would otherwise remain hidden forever. This leads us to the threshold of discovery. For decades, the existence of gravitational waves was accepted in theory, confirmed indirectly by the slow dance of neutron stars, whose orbits shrank exactly as predicted. But no one had yet touched them directly. No one had yet felt the tremor of spacetime itself. To achieve that would require an instrument unlike any built before, one capable of measuring changes in length so small they defy imagination. Humanity would try, and against the odds, succeed. The story of gravity bending itself is therefore not just theoretical. It is real, and it is something we have now heard with our own instruments. The universe spoke through the ripples of space-time, and for the first time in history, we listened. The idea of gravity acting upon itself long seemed too exotic to believe, and yet the cosmos provided hints, faint at first, but undeniable. In the 1970s, two astronomers, Russell Hulse and Joseph Taylor, discussed a system unlike any known before. It was a binary pulsar, two neutron stars locked in a dizzying orbit around one another. Neutron stars are the remnants of massive suns, collapsed to spheres a dozen kilometers across, yet so dense that a single teaspoon of their matter would outweigh a mountain. Their orbits around one another were measured with exquisite precision by tracking the radio pulses emitted from one of the stars. Over years of observation, Hulse and Taylor found that the orbit was shrinking. The stars were drawing ever closer in a slow spiral. No force in Newton's universe could explain this, but in Einstein's it was expected. The system was radiating energy away as gravitational waves, ripples of space-time itself, carrying energy into the cosmos. The rate of orbital decay matched Einstein's equations perfectly. It was as though the binary was whispering to us across the light years, confirming that gravity can ripple, that it can bend itself into waves. This discovery earned the Nobel Prize, for it was the first firm evidence that gravitational waves were more than abstractions. Still, whispers are not the same as a song. Indirect evidence was powerful, but incomplete. Physicists yearned for direct detection, for the actual tremor of space-time to be measured on Earth. The challenge seemed impossible. The ripples that reach our planet from distant collisions stretch and compress distances by less than 1,000th of the diameter of a proton. No ruler, no telescope, no ordinary device could detect such as. Yet the ambition grew. The idea was deceptively simple. If a gravitational wave passes through Earth, it will stretch space in one direction, while compressing it in another. If long tunnels are placed at right angles to each other, with laser beams bouncing back and forth inside them, the passing wave would change the distances in those tunnels ever so slightly, altering the interference of the light. The pattern would shift, revealing the passage of the wave. This idea became reality in the form of the Laser Interferometer Gravitational Wave Observatory, or LIGO. Constructed with arms 4 kilometers long, its mirrors polished to impossible vision, its lasers stabilized against the faintest vibrations. LIGO was designed to listen to the universe in a way no instrument ever had. The noise of trucks, the tremor of earthquakes, even the footsteps of workers could overwhelm the signal. And so every detail was refined to isolate the faintest possible whisper of space-time. For years, the detectors listened and heard nothing but silence. Many wondered if the dream was futile. Yet persistence drove the project forward. Upgrades refined the sensitivity, and hope remained that somewhere depths of space, two massive objects were spiraling together and would send their waves our way. Then, in September of 2015, the silence broke. The signal was brief, less than a second long. It was the final dance of two black holes, each about 30 times the mass of our sun, merging more than 1 billion light-years away. The waves reached Earth after traveling across cosmic time, stretching and compressing space-time itself as they passed through the detectors. For the first time, humanity had heard the bending gravity. The signal matched Einstein's predictions exactly. The chirp of the black hole's merger confirmed that gravity is not just the curvature of space-time, but a living fabric capable of rippling across the universe. In that moment, general relativity affirmed in its most daring prediction, and a new era of astronomy began. This was gravity not only bending light, not only guiding planets, but bending its, sending out ripples that spoke catastrophic collisions in places no light could ever reach. Black holes merging in darkness had become visible not with eyes, but with ears attuned to space-time. The discovery was a triumph not only of theory but of perseverance, of decades of work, by thousands of scientists and engineers who trusted Einstein's equations enough to build an instrument sensitive to tremors in the fabric of reality. It proved beyond doubt that gravity acts on itself, bending and rippling, carrying information across the cosmos at the speed of light. But this discovery also raised new questions. If gravity can ripple, how else can it behave? Can it twist and fold in ways we have not yet imagined? And if light and gravity both bend, do they bend in the same way? Or does gravity conceal deeper layers of reality yet to be uncovered? The faint chirp that reached Earth in 2015 was more than a scientific milestone. It was the first voice of the universe in a language older than light. For billions of years, those waves had traveled silently, unaffected by dust or gas, untouched by the obstacles that blur or block starlight. When they finally brushed against our planet, they left a trace so slight it could be measured only by an instrument built with almost impossible precision. Yet within that trace lay the memory of two black holes colliding in darkness. Humanity heard space-time itself ring like a bell. This was not a single triumph, but the opening of a new sense. Until then, astronomy had been almost entirely visual. We studied stars by their light, galaxies by their glow, nebulae by their colors. Even when we extended our view to radio waves or X-rays, we were still working with photons, with messengers of electromagnetism. Now we had a new messenger, one not come from outside space-time, but space-time itself. Gravitational waves opened a window that no photon could provide. The discoveries multiplied. More black hole mergers were heard, each signal unique, each telling a story of masses and spins and distances. Then came the detection of two neutron stars colliding. The event was accompanied not only by gravitational waves but by light across the spectrum, from gamma rays to radio waves. For the first time, the cosmos gave us both sight and sound of the same event. The waves carried the imprint of the star's spiral, while the light revealed the fireball of Ella flung outward. Heavy atoms like gold and platinum were formed in that collision, seeding the universe with the materials that would one day form planets, people. Through these detections, the nonlinear nature of Einstein's equations became undeniable. Gravity does not simply curve around matter. It can carry away energy. It can transmit information. It can act back upon itself in ways Newton could never have imagined. The waves we now observe are the proof that gravity bends, not in the way light bends through glass or on stars, but in a deeper sense. It is the bending of the fabric of reality, shaking itself loose, and sending ripples into the void. Each signal detected by LIGO and later by other observatories like Virgo is a reminder that the universe is restless. Black holes collide, neutron stars spiral inward, entire galaxies merge, and through all of it, space-time ripples. These waves faint by the time they reach us, yet they are everywhere. The Earth is awash in them, passing unnoticed through our bodies, through the planet, through the atmosphere. Only our instruments, fine-tuned and patient, reveal their presence. And so we come to a new understanding. Gravity is not just the geometry of space-time shaped by mass. It is dynamic, alive, capable of bending and bending again, producing waves that travel freely through the cosmos. To ask whether gravity bends is no longer a question of speculation. The answer is written in the data, recorded in the trembling of mirrors, confirmed in the mathematics that has never yet failed. But this answer leads to another. If gravity can ripple outward, what happens in the most extreme environments, where space-time is bent to its breaking point? Black holes have given us waves and whispers. At their centers lie singularities, places where our understanding falters. To explore whether gravity can fold entirely in upon itself, to see whether the bending has a limit, we must venture into the realm of black holes. On a quiet morning in September of 2015, a faint vibration passed through Earth. It was not felt by people, nor by animals, nor even by the most sensitive seismographs. It was too subtle for ordinary instruments, stretching and squeezing space itself by less than the width of a proton. Yet in two long tunnels in Louisiana and Washington, beams of laser light noticed. They flickered, shifted, and sang the first note of a cosmic chorus. Humanity had, for the first time, heard the ripples of space-time itself. The story of this moment is as much about patience as it is about discovery. For a century after Einstein's prediction of gravitational waves, no one could be sure they would ever be measured. The waves were real in the mathematics, confirmed indirectly by the slow spiraling of neutron stars, but to catch them directly seemed impossible. They passed through planets and stars as though through air, leaving only the tiniest mark. To hear them, scientists had to build machines capable of detecting distortions smaller than anything ever attempted, changes in distance thousands of times smaller than the nucleus of an atom. This machine, LIGO, the Laser Interferometer Gravitational Wave Observatory. It was not one but two instruments, separated by thousands of kilometers, each with arms 4 kilometers long. Lasers bounced between vacuum tubes, comparing distances with impossible accuracy. When a gravitational wave passed, it would stretch one arm and compress the other, shifting the interference pattern of the light. By comparing the signals from both detectors, scientists could confirm that what they heard was not local noise, but a true tremor of space-time sweeping across Earth. The signal they caught came from the death spiral of two black holes. Each one was about 30 times the mass of the Sun, locked in orbit around one another more than 1 billion light-years away. For millions of years they had circled, but as they lost energy through gravitational waves, they drew closer and closer, until, in their final seconds, they whirled at nearly the speed of light before colliding and merging into one. The collision released an energy equivalent to several converted entirely into gravitational waves in a fraction of a second. It was this storm of curvature that traveled across the universe and reached Earth on that September morning. The waveform recorded by LIGO was distinctive. It began as a low thrum, rising in pitch and amplitude as the black holes spiraled faster, ending in a sharp chirp as they merged. In less than a second, the detectors had captured a story written over billions of years and billions of light-years, carried faithfully across the void by space-time itself. When the announcement came in February of 2016, the scientific world and the public alike were electrified. The discovery was hailed as one of the greatest of our age, confirming Einstein's prediction from 1916 and opening a new era of astronomy. For the first time, we had more than sight. We had hearing. The universe had been silent to us. Now we could listen to its deepest cataclysms. The confirmation was not just about proving a theory. It was about expanding the very toolkit of humanity. Telescopes show us photons, the messengers of light. Photons are easily scattered or absorbed. Gravitational waves, by contrast, pass unhindered through matter. They are messengers that cannot be blocked, carrying pristine information from the heart of black hole collisions, from the core supernovae, perhaps even from the first instant of the universe itself. This is what it means to speak of gravity bending. Not the bending of lines or beams, but the bending of space-time so profound that it ripples outward, a message written in the curvature itself. The universe is not static but dynamic, a sea whose waves we are only now beginning to hear. The first detection was the dawn. More waves would follow, each carrying new lessons, each proving that space-time not only curved, but alive with motion. The silence once broken did not return. After that first chirp in 2015, the universe continued to send its messages, and the detectors kept listening. More black hole mergers followed, each with its own unique song. Some involved giants of times the mass of our sun, others paired small holes, but all told the same truth. Space-time itself was rippling, gravity was bending, not as a distortion of light or as the path of planets, but as pure waves of geometry traveling freely across the cosmos. Each new detection added confidence. Waveforms matched the predictions of Einstein's equations with uncanny precision. The rise and fall of frequency, the sharp final chirps, the exact timing between the detectors, separated by thousands of kilometers, all lined up. The mathematics that had once seemed impossible to test was now confirmed again and again by the universe itself. With every signal, general relativity stood unshaken, its vision of gravity as the curvature of space-time rippling outward affirmed. Then came an even more extraordinary event. In August of 2017, LIGO and its European partner Virgo read the merger of two neutron stars. Unlike black holes, neutron stars are made of matter, and when collided, the explosion produced not only gravitational waves, but a burst of light across the spectrum. Within seconds, gamma-ray telescopes detected a flash. Hours later, optical telescopes found the afterglow. Over days and weeks, astronomers tracked the fading light as heavy elements like gold and platinum were formed in the fiery debris. For the first time, the universe revealed itself in both sound and sight. Gravitational waves carried the story of the spiral and collision, while light carried the story of the explosion that followed. Together they created a symphony of information, confirming theories about the origin of heavy elements and showing that neutron star mergers were among the most violent factories of the cosmos. The implications were staggering. With gravitational waves, we could probe places that had been hidden, places where light could not escape. Black hole mergers, invisible to ordinary telescopes, now revealed themselves through their ripples. With neutron star mergers, we could study not only the ripples, but also the light, giving us a fuller picture of cosmic events than ever before. The field of multi-messenger astronomy was born, where gravitational waves and light joined forces to tell the same story from different angles. Each detection sharpened our understanding. We learned about the masses and spins of black holes, about the stiffness of neutron star matter, about the rate the universe expands. Gravitational waves were not only a proof of Einstein's vision, they were tools for measuring the cosmos, and clocks carried on the trembling fabric of space-time. And yet, amid all this triumph, the deeper question lingered. If space-time can ripple, what does this mean about the nature of gravity itself? Is it simply geometry reacting to mass and energy? Or is there something more fundamental beneath waves, perhaps particles or quanta, that carry the interaction? The bending of gravity revealed by these detections was real, yet it hinted at mysteries beyond our reach. For now, what mattered was that we had learned to listen. The cosmos is filled with whispers and roars of merging objects, with ripples from ancient collisions still washing across us. The detectors that captured them are humanity's ear in the universe, showing that gravity bends not only in curves but in music. And in that music lies the chance to glimpse truths far deeper than we have yet imagined. The universe has always spoken, but only in recent years have we built the tools to hear it. Ripple caught by LIGO or Virgo is like a note struck on a cosmic instrument, a reminder that gravity does not rest silently as a background age. It moves, it vibrates, it carries energy across the immensity of space. When we listen to these waves, we are listening not to something carried by space, but to space-time itself in motion. The beauty of this discovery is that it confirmed not only that Einstein's equations were correct, but that they were daringly complete. In 1916, when Einstein first tested that accelerating masses would radiate waves of curvature, even he doubted whether the effect could ever be measured. The mathematics was sound, but the ripples seemed impossibly faint. A century later, the universe proved his intuition right, and his doubts wrong. The faintest tremors in space-time were heard, and the sound matched his prediction to perfection. In the aftermath of the first instance, scientists realized they had crossed a boundary as profound as when Galileo first turned his telescope to the heavens. Before Galileo, the sky was a tapestry of points, fixed and eternal. With a telescope, the moon showed mountains, Jupiter revealed moons, Saturn displayed rings, and the universe was transformed from static perfection to dynamic reality. In the same way, before LIGO, the universe seemed a place revealed only by light. Now it revealed itself in vibrations. The cosmos grew more intimate, more alive, more full of hidden drama. These ripples are not gentle waves lapping at the edge of a pond. They are born of violence beyond comprehension. Black holes collide with energies that outshine all the stars of the observable universe for an instant. Neutron stars smash together in explosions that scatter the heaviest elements into the void. And yet, by the time the waves reach us, they are faint whispers, stretching space by less than a fraction of an atom. That we can hear them at all is a testament to human ingenuity, to our ability to build instruments so precise that they can detect the heartbeat of the cosmos itself. But even to celebrate this achievement, we must recognize the depth of what it implies. Gravitational waves prove that gravity bends not in the simple sense of light refracting through water or curving near a star, but in the profound sense of space-time itself, rippling. This bending is not of paths but of the stage, not of travelers but of the road. It shows us that gravity is not static, it is dynamic, self-interacting, capable of carrying its own echoes across the universe. And so we come to the heart of the question. If light bends when it follows curved space-time, and if gravity bends by rippling space-time, do they bend in the same way? Can we compare the curve of a beam of light of the sun with the ripple of a gravitational wave across billions of light years? The answer is subtle. For light bends as a passenger, gravity bends as the driver. Light traces the shape that already exists, while gravity sculpts the shape itself. To understand this comparison, to see how light and gravity mirror and yet differ from each other, we must look more closely at their behavior, side by side. Only then can we begin to answer whether gravity bends like light, or whether its bending belongs to a deeper, more fundamental order of reality. Light has always been our guide to the universe. From the glow of the sun to the faintest shimmer of galaxies at the edge of the observable cosmos, it is light that tells us what is there. Gravity, in contrast, has been our anchor, holding Earth's oceans, binding planets to stars, stars to galaxies, and galaxies to clusters. One we see, the other we feel. Yet Einstein's vision reveals that both are woven into the same fabric of space-time. Both light and gravity are not free agents, but obedient travelers, bound to the same cosmic geometry. And so the question naturally arises. When we say light bends, and when we say gravity bends, are we speaking of the same thing? Or are they two very different stories that merely share the same word? When light passes near a massive object, it curves. This bending can be seen in gravitational lensing, in the shifted positions of stars near the sun during an eclipse, in the arcs of galaxies stretched around invisible clusters of dark matter. The photon does not resist, does not hesitate, because for the photon, there is no choice. It is following the straightest possible line, the geodesic carved by space-time itself. To us, watching from the outside, the path looks curved, but to the photon, it is as natural and direct as a straight road. Light bends because space-time curves. Gravity, however, bends differently. It is not a traveler, but the very geometry through which light and matter move. Two black holes spiral into each other. The curvature does not remain still. It ripples outward. Those ripples are gravitational waves, distortions of spaced self, stretching and compressing distances as they pass. If light's bending is a response, gravity's bending is an action. One reveals the shape, the other creates the change. Yet, there is kinship. Both light and gravity are limited by the same cosmic speed. No signal can outrun them. Gravitational waves, though most violent collisions, travel faster than light. They move at the ultimate limit set the universe, carrying information across billions of light years with perfect fidelity. In this way, light and gravity share a rhythm, each bound to the same speed, woven into the fabric of reality. Consider again that mirage, where layers of hot and cool air bend sunlight into illusions of distant water. Now imagine a gravitational mirage, where a cluster of galaxies bends light into arcs and rings, the result of light tracing paths shaped by its environment, whether air or space-time. But when two black holes merge and send gravitational waves outward, there is no passenger following a shaped path. Instead, the shape itself is changing, the stage itself trembling. Light bends within the play. Gravity bends the theater itself. To put it differently, light tells us about geometry, while gravity is geometry. Light's bending is a window. Gravity's bending is the frame. And yet the two phenomena are inseparable. For without gravity, there would be no curved paths for light to reveal. And without light, there would be no rest to the bending of space-time at all. It is tempting to imagine that light and gravity are simply two sides of the same coin. Both are waves. Both travel at the same speed. Both can be bent or shaped by the geometry of space-time. But then nature remains distinct. Light is carried by photons, the quanta of the electromagnetic field. Gravity, if it has a quantum particle, would be carried by gravitons, which have never been observed. Light is blocked, scattered, absorbed. Gravitational waves pass through matter unimpeded, carrying messages from places light cannot escape. So when we ask if gravity bends like light, the answer is both yes and no. Yes, in that both respond to the structure of space-time, both trace or transmit curvature. But no, in that gravity is not a traveler through geometry, but the very essence of geometry itself. Light bends in obedience. Gravity bends in command. And it is in the extremes, in the realms where black holes warp reality beyond recognition, that these differences become clearest. To truly see how gravity bends, we must venture into depths of those cosmic abysses, where light is trapped, but where gravity continues to rule with uncompromising authority. Light's bending is familiar to us in a way that gravity's bending is not. We see it in the lift of a pencil in a glass of water, in the shimmer of a rainbow, in the distorted arcs of galaxies magnified by unseen clusters. These are visual, immediate, woven in our experience of the world. Gravity's bending, however, is subtle, not visible to the naked eye, not something senses evolved to perceive. We never wake in the morning and feel space-time stretch around us. We cannot look at the night sky and see the waves of gravity sweeping through. And yet they are there, everywhere, passing silently through our planet, unnoticed, until instruments reveal them. This difference makes light and gravity complementary. Light offers clarity and precision, but it is limited. Photons scatter in clouds. They are absorbed by dust. They are blocked by walls of matter. Gravity is weak compared to light, but in that weakness lies its gift. Gravitational waves pass through everything, carrying their story unbroken from the heart of collisions, where no light escapes. Where light fails, gravity succeeds. Where gravity is faint, light provides detail. Together, create a fuller picture of the cosmos than either could alone. But their relationship is not only complementary, it is also bound by the same cosmic law. Both are limited by the same speed. When the merger of neutron stars was detected in 2017, gravitational waves and gamma rays arrived at Earth within seconds of each other, traveling for more than 100 million years. The near-perfect agreement confirmed that gravity and light move through the cosmos with the same ultimate speed. This is not coincidence, but necessity. If one were faster than the other, causality itself would unravel, and Einstein's vision would collapse. Harmony of their speeds is proof of the deep unity of physical law, and yet unity does not mean sameness. Light bends when space-time curves, but it never changes the curvature on its own. It is a witness, a messenger, tracer of geometry. Gravity, in contrast, bends because it is geometry, and it changes itself. When black holes merge, the ripples of space-time they send out are not carried by photons. They are not images or reflections. They are reality itself shaking. Imagine standing on a shoreline. Light is like the reflection of the moon on the surface of the water, a beautiful tracer of what is there, dependent on the waves and currents to shape it. Gravity is the tide, and the waves themselves, rise and fall of the ocean, that the reflection cannot exist without. The reflection bends because the surface bends, but the surface bends on its own, whether or not the moonlight ever touches it. This distinction is subtle, but it is central to the question we are asking. Does gravity bend like light? Not quite. Light bends when something else shapes path. Gravity bends because it is the shaping. Light's obedience shows us the map of space-time. Gravity's rippling shows us that the map itself is alive, changing, carrying its own stories across the cosmos. This realization draws us inexorably toward the most extreme places in the universe, the laboratories where both light and gravity reveal their limits. Black holes are those places, the ultimate proving grounds, where light is trapped and gravity folds space-time into horizons and singularities. If we want to know what it truly means for gravity to bend, we must enter the shadowed domain of these cosmic abysses, where the differences between light and gravity become most stark, and where our understanding begins to falter. In the end, comparing light and gravity is like comparing a traveler to the road itself. Light journeys along space-time, tracing the straightest possible line, revealing the contours of alleys and the slopes of hills, carved into the fabric by mass and energy. Gravity is those valleys and hills. It is the geometry that light cannot help but follow. The two are forever linked, yet their roles are fundamentally different. One is the messenger, the other is the message. This difference becomes starkest in the realm of extremes. When light passes near a massive star, it bends gracefully around it, allowing us to glimpse the geometry sculpted by the star's mass. But when black holes collide, light is absent. No photon can escape. Here only gravity speaks, and it speaks in waves that ripple upward through space-time. Light cannot tell us what happens inside the shadow, but gravity's bending carries the story beyond the horizon. The stage and the performance are one, and the waves that reach us are the stage itself in motion. And yet, for all their differences, light and gravity share a strange kinship. Both move at the same ultimate speed, both travel across the same immensity, both obey the same geometry. When light bends, it shows us where gravity has shaped the path. When gravity bends, it tells us that the path itself is changing. Together they reveal a universe that is not static but dynamic, not empty, but alive with curvature and ripple. We might ask whether one is more fundamental than the other. Is gravity the deeper truth, the architect of reality, while light is only its tracer? Or is the distinction illusory, with both belonging to a single, unified work we have not yet discovered? These questions lure at the edge of modern physics, where quantum mechanics and relativity struggle to meet. Now, we can say this much with certainty. Light bends because space-time curves, and gravity bends because space-time can ripple. They are not the same, yet both are essential to our understanding of the cosmos. Without light, we could not see the curves. Without gravity, there would be no curves at all. And so the journey continues. For there is one place where the bending of light and gravity reaches its limit, where fabric folds so severely that not even photons can find a way out. These are the black holes, the ultimate expressions of curved space-time, where light is trapped in orbit and gravity rules unchallenged. If we wish to know whether gravity can truly bend upon itself to the point of breaking, it is into these dark realms that we must venture. There are places in the universe where the bending of space-time becomes absolute. The geometry folds inward so severely that nothing, not even light, can escape. These are black holes, the ultimate expressions of gravity. They are not merely massive stars, collapsed into dense remnants. They are boundaries of knowledge, edges where our understanding falters, horizons beyond which time and space themselves are sealed away. The story of black holes begins with the collapse of stars. A massive sun burns its fuel, fusing hydrogen into helium, helium into heavier elements, fighting against gravity with the pressure of nuclear fire. But when that fire is exhausted, gravity wins. The star collapses inward. For some, the collapse halts as a white dwarf or a neutron star, supported by the quantum resistance of matter itself. But if the mass is too great, no force can withstand the pull. The collapse continues without end, compressing all matter into a singularity, a point where density and curvature are infinite, where space-time is bent beyond recognition. Surrounding this singularity is the event horizon, the ultimate boundary. It is not a surface in the ordinary sense, but a point of no return. Cross it, and all possible paths lead inward. Light that tries to escape is pulled back, not because a force drags on it, but because the geometry of space-time itself curves inward. The horizon is where straight lines no longer point outward. From the outside, it is a perfect darkness, a sphere from which nothing can emerge. To describe a black hole is to describe space-time, twisted into its most extreme form. Around the horizon, light can be bent into orbits, circling endlessly in rings of fire. Beyond that lies the accretion disk, matter spiraling inward, heating to millions of degrees as it crashes toward the abyss, emitting X-rays that we can detect with telescopes. Jets of plasma shoot outward along magnetic fields, streaming for thousands of light years. These are the signs by which we know black holes exist, even though the holes themselves remain invisible. But the true wonder of black holes is not in their violent surroundings. It is in what they tell us about gravity itself. Here, space-time is not gently curved as around a planet or a star. It is folded inward infinitely. The singularity at the core is a place where Einstein's equations down, where the curvature grows without bound, and the laws of physics, as we know them, cease to function. Gravity, in bending itself, reaches a point of self-destruction. This is where the question becomes unavoidable. Does gravity truly bend without limit, or does something deeper intervene? The singularity is not a place we can see. It is hidden behind the horizon, shielded from view, but it is also a place where our theories falter, where relativity alone cannot provide the answer. To understand what lies at the heart of a black hole, we need a new framework, one that unites gravity with quantum mechanics. Until that day, we explore what we can. Black holes are not entirely silent. They can merge, sending gravitational waves across the cosmos, waves we have not detected. They can bend light around them, creating gravitational lenses so powerful they multiply the images of distant galaxies. They can even reveal their silhouettes, as the Event Horizon Telescope has shown, capture a glowing ring of matter around the shadow of a supermassive black hole. These observations remind us that black holes are not just exotic oddities. They are laboratories of gravity. They show us what happens when curvature becomes extreme, when space-time bends upon itself beyond any earthly comparison. They're both proof and puzzle, confirming Einstein's vision while also revealing its limits. And so, when we ask whether gravity bends, the black hole answers with both silence and song. Silence, because nothing escapes from within its horizon. Song, because the ripples it sends across the universe testify its existence. Here, in these dark realms, gravity is not a stage, but also the actor, the playwright, and the mystery. It bends light, it bends time, it bends itself, till bending becomes collapse. Yet even black holes may not be the end of the story. For if gravity bends to the point of singularity, then we must confront the question of whether our understanding is incomplete. Perhaps gravity has a quantum nature, hidden beneath the fabric we know. Perhaps the singularity is not an infinite point, but a door to a deeper theory. To search for that theory is to step into the puzzle that has haunted physics for a century, the riddle of quantum gravity. Near the edge of a black hole lies one of the strangest features in all of physics, the event horizon. Unlike the solid surface of a star or a planet, it is intangible. Not touch it, nor would you notice any physical barrier as you passed across it. Yet from that moment onward, the universe outside would vanish forever. The horizon is the place where all possible future paths point inward. To an observer far away, time at the horizon appears to freeze, light emitted from the edge, stretching into infinite red as it struggles to escape. To the traveler falling in, however, time flows normally. The difference is perspective, shaped entirely by the geometry of space-time. Orbiting the horizon is the photosphere, a place where light can surf endlessly. Here, gravity bends paths so sharply that a photon can be trapped in orbit, circling the black hole in a perpetual loop. In practice, these orbits are unstable. A tiny nudge sends the photon inward to the singularity or outward into space. But their very existence shows the extremity of curvature. Space is bent so profoundly that even light, which elsewhere speeds unchallenged, can be bound into endless circuits. Farther out lies the accretion disk, a swirling torrent of gas and dust, heated to millions of degrees as it spirals inward. The particles collide and compress, emitting X-rays and gamma rays that blaze with a brightness greater than entire galaxies. Jets erupt from the poles, beams of plasma shot outward at near the speed of light, power the rotation of the black hole itself and the magnetic fields in the surrounding disk. These colossal structures stretch for thousands of light years, a reminder that even in their silence, black holes shape the universe around them. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy M87, a monster 6.5 billion times the mass of the Sun. The glowing ring surrounding its darkness was the emission of matter, heated as it fell inward, bent into a circle space-time itself. That ring, the silhouette of the horizon, was not an artist's concept, but a photograph of gravity at its most extreme. It was as though the universe had allowed us to peer, just for a moment, into its deepest secret. But the image raised as many questions as it answered. At the center, hidden from sight, the singularity remains unresolved. Einstein's equations tell us that matter collapses into an infinitely dense point, a place where curvature becomes infinite, where time and space lose all meaning. Yet infinities are signs not of truth but of limitation. They are the marks of a theory pushed beyond its domain. Just as Newton's mechanics fail at the speed of light, general relativity may fail at the singularity. Something more must take its place. Black holes are paradoxes. They are predicted by general relativity, yet they also reveal its boundaries. They are prisons from which nothing escapes. They can merge and release vast amounts of energy as gravitational waves. They conceal singularities, yet they also give rise to horizons that can be mapped and measured. They are silent, yet they shape galaxies, influencing the formation of stars and the evolution of cosmic structure. For all contradictions, black holes are the clearest demonstration that gravity bends in ways no force does. They show us not only that space-time curves, but that it can fold upon itself. The very notion of space and time breaks down. In their shadows lies the proof that gravity is not a force in the old sense, but the architecture of reality itself. And yet, If we understand black holes fully, we must confront the puzzle they pose. What happens to information that falls inside? Does it vanish, violating rules of quantum mechanics, or is it preserved somehow on the horizon? Is the singularity a true point of infinite curvature, or is it resolved by a deeper layer of physics? To answer these questions, we must move beyond Einstein into a realm where gravity meets quantum mechanics. At the heart of a black hole lies the most unsettling mystery in physics. According to Einstein's equations, all the mass collapses into a singularity, a point of infinite density where curvature grows without bound. But infinities are not physical things. They are the warning signs of a theory breaking down. Just as Newton's laws fail when speeds approach that of light, general relativity fails in the core black hole. It is as if the mathematics itself is telling us that our description of reality is incomplete. Physicists wrestle with this paradox. On the one hand, black holes are among the most reliable predictions of relativity. We have observed their gravitational effects on stars, seen the light bent into glowing rings around their horizons, and detected the waves they send when they collide. On the other hand, the singularity they contain defies all understanding. If gravity is the bending of space-time, then inside the horizon, we must confront the question of what happens when the bending never ends. Can space-time fold infinitely, or is there a deeper structure waiting to be uncovered? One clue comes from quantum mechanics. The laws of the very small forbid certain infinities. Particles cannot be confined to a point without their energies becoming unbounded. Quantum rules suggest that there must be a new description of what happens when matter is compressed beyond any limit. Perhaps the singularity is not a true point, but a new state of matter. Or perhaps space-time itself is quantized, with a smallest possible scale, beyond which it cannot be bent. Without such a theory, we are left with a contradiction. Relativity predicts what it cannot describe. Black holes also pose the puzzle of information. According to relativity, anything that crosses the event horizon is lost forever. According to quantum mechanics, information can never be destroyed. The clash of these principles has led to decades of debate, with proposals ranging from information being stored on the horizon to the possibility that it is released through subtle radiation. Stephen Hawking showed that black holes are not entirely black. They emit a faint thermal glow, now known as Hawking radiation, as quantum effects near the horizon allow particles to escape. Over unimaginable spans of time, this radiation would cause black holes to evaporate. But if they disappear completely, what happens to the information of what fell inside? This is not a philosophical puzzle. It is a sign that our two greatest theories, general relativity and quantum mechanics, cannot both be the final word. Black holes stand at the crossroads, showing us where the bending of gravity pushes relativity to its breaking point and demands a new framework. They are cosmic laboratories, revealing the limits of our knowledge and pointing us toward a deeper truth. To study black holes is to look at the sharpest edge of reality. They remind us that gravity is not just a gentle curve, but a force that can fold space-time, so absolutely that time and space themselves are reshaped. They reveal the unity and the conflict of our theories, showing us that while relativity explains the large and quantum mechanics explains the small, neither alone can explain the singularity. And so, as we leave the realm of black holes, we face the next great question. If gravity bends beyond relativity's reach, then we ask how it bends when quantum rules are applied. Does space-time ripple in discrete quanta carried by particles we have not yet observed? Can the fabric of reality itself be unified with the strange probabilities of the quantum world? To explore this frontier is to begin the search for quantum gravity, the puzzle that may finally explain what it means for gravity to bend. The bending of light we can see, the bending of gravity we can now hear. But to understand whether gravity truly bends in the deepest sense, we must leave the realm of black holes and enter the strange domain of the quantum. For it is here, in the world of particles and probabilities, that Einstein's vision collides with the laws of the very small. General relativity tells gravity is geometry, the curvature of space-time itself. Quantum mechanics tells us that everything, from light to matter, is quantized into packets particles, and fields. Reconciling these visions is the greatest challenge of modern physics. At ordinary scales, there is no conflict. Planets orbit the Sun exactly as relativity predicts. Atoms bind together as quantum mechanics describes. In the extremes, near singularities, or in the first moments after the Big Bang, both sets of rules must apply at once, and there they clash. Relativity is smooth and continuous. Quantum mechanics is discrete and probabilistic. When we try to calculate what happens to space itself at the smallest scales, infinities erupt, equations break down, and certainty dissolves. If gravity bends, perhaps it bends smoothly, but in quanta, the way light is carried, not as a continuous wave, but in photons. Physicists have long speculated about a particle called the graviton, the hypothetical quantum of the gravitational field. If photons are the quanta of light, and gluons the quanta of strong force, then gravitons would be the quanta of space-time, curvature itself. They would be massless, traveling at the speed of light, carrying the interaction of gravity across the cosmos. But gravitons have never been observed, and they may never be. Gravity is extraordinarily weak compared to the other forces. A single magnet could a paperclip against the pull of the entire Earth. To detect a graviton would require an instrument larger than a planet, and even then, the chance would be vanishingly small. The existence of gravitons remains an idea, a mathematical possibility, not yet a physical discovery. Still, the search for a quantum theory of gravity continues. One approach is string theory, which imagines that all particles are not points, but tiny vibrating strings. Different vibrations produce different particles, and among them naturally emerges a graviton. In this vision, gravity's quantum nature is built into the very fabric of the theory. Another approach is loop quantum gravity, which suggests that spacetime itself is quantized, made of tiny loops woven into a network. In this picture, bending spacetime is not continuous at all, but granular, with the smooth curves of relativity emerging only when the loops are averaged over large scales. Both approaches are ambitious, elegant, and incomplete. Neither has yet provided a testable prediction that distinguishes it from the others. Both aim to solve the same riddle. How does gravity bend when quantum rules apply? Is spacetime smooth or discrete? Is curvature continuous or built of quanta? Until we know, the question of gravity's deepest bending remains unanswered. Black holes sharpen this puzzle at its edge. Inside the horizon, relativity predicts singularity. Quantum mechanics insists that infinities cannot exist. Where, in a theory we do not yet possess, the two visions must merge. Perhaps singularities do not exist at all. Perhaps they are replaced by quantum states of spacetime, regions where the fabric is compressed but not infinite, bent but not broken. If so, then gravity bends in ways we cannot yet describe, language we have not yet learned. What makes this pursuit so profound is that it is not only about black holes, it is about the universe itself. The Big Bang, the origin of all things, was a moment of infinite density, a singularity on the largest scale. To understand how gravity bends at quantum level is to understand the birth of the cosmos. The search for quantum gravity is therefore the search for our own beginning, the attempt to replace infinities with explanations, paradoxes with clarity, and so the question remains open. Does gravity bend in quanta? Are there gravitons waiting to be discovered? Particles whispering across spacetime with every ripple? Or is the very concept of particles incomplete, replaced by a deeper framework that unites quantum mechanics and relativity in ways we have yet imagined? Until we know, we live in the tension between two great visions, each powerful, each incomplete, each waiting for the other to yield. The dream of unifying gravity with quantum mechanics has haunted physics for more than a century. Each success in one domain seems to highlight the absence of the other. Relativity reigns over the vast, describing galaxies, stars, and the bending of space-time with flawless accuracy. Quantum mechanics rules the minute, predicting the behavior of particles and fields with astonishing precision. But when the two are brought together, when we try to describe the curvature of space-time at the smallest possible scales, the mathematics unravels into infinities that cannot be tamed. One vision imagines space-time itself as quantized. Loop quantum gravity proposes that the fabric of the universe is woven from tiny loops, discrete chunks of geometry that can be counted. In this picture, there is no smooth continuum. Instead, areas and volumes are made of indivisible units, like pixels on a screen that only smooth from far away. When gravity bends in this framework, it bends not continuously, but step by step, grain by grain. Singularities may never form, for the loop prevents space-time from compressing beyond a finite limit. The smooth arcs of relativity are approximations, like a curved line drawn from many segments. Another vision sees particles not as points but as strings, vibrating at scales far smaller than atoms. In string theory, each mode of vibration corresponds to a different particle, and among these naturally arises the graviton. Here, gravity's bending is the result of strings interacting, weaving geometry from vibration itself. String theory is ambitious, uniting all forces into a single framework, but it remains distant from experimental test. Its mathematics is rich, but its predictions are elusive. Physicists have sought clues in the cosmos itself. The earliest moments after the Big Bang may have left imprints of quantum gravity in the cosmic microwave background, faint patterns that reveal how space-time behaved at unimaginably high energies. Gravitational waves may also carry signatures of quantum effects, subtle deviations from Einstein's predictions that could point to new physics. Black holes, too, may reveal the answer. Their horizons, their radiation, and the fate of their singularities all be shaped by quantum gravity in ways we have not yet observed. But the difficulty is staggering. The scales where quantum gravity dominates are so far beyond reach that no particle collider, no telescope, no laboratory experiment has yet touched them. We are left to infer, to guess, to build theories that may remain untested for generations. And progress comes, not in leaps but in the quiet narrowing of probabilities, in the discovery of what could be true. Each failed attempt clears the path. Each paradox sharpens question. One such paradox is the black hole information problem. If information is in black holes, quantum mechanics is violated. If it is preserved, then relativity must be incomplete. Some theories suggest that information is encoded on the event horizon itself, stored like a hologram on a two-dimensional surface that describes a three-dimensional volume. This holographic principle hints that gravity and space-time may themselves be emergent, born from quantum rules in a deeper reality. In this view, the bending of gravity is not fundamental at all, but a collective illusion, like pulls of a wave emerging from countless molecules of water. This idea carries profound implications. Space-time and gravity emerge from quantum mechanics. Then gravity bending is not a basic law, but a consequence of something even deeper. It may be we call curvature is the large-scale behavior of quantum entanglement, the mysterious connections between particles that defy classical space and time. The geometry we see, the bending we measure, could be the visible shadow of an underlying quantum web. Such thoughts remain speculative, yet they capture the imagination because they offer a path forward. The bending of gravity that Einstein described may be only the first layer of truth. Beneath it may lie the quanta of geometry, the strings of vibration, or the holographic codes of entanglement. Until we discover which, we live at the boundary of knowledge. The smooth curves of space-time dissolve into the grainy probabilities of the quantum world. And still, experiments press on. LIGO and Virgo listen for ripples in time. Particle colliders push toward higher energies. Telescopes gaze into the afterglow of the Big Bang. Each observation has the potential to reveal a hint, a deviation. A whisper tells us how gravity bends when quantum rules are obeyed. The puzzle remains unsolved, but in its very difficulty lies its importance. For if we can answer how gravity bends in the quantum world, we will not only complete Einstein's vision, we will glimpse the foundation of reality itself. In the quest to understand how